The ocean covers 71% of our planet. It contains 97% of Earth's water. It's home to over 2 million species, though we've only identified about 250,000 of them. Every breath you take, every second breath comes from the ocean. Yet despite living on a blue planet, most of us know almost nothing about the sea. Did you know the ocean has waves taller than 10-story buildings that never break? That there are underwater waterfalls thousands of feet high? That some fish can walk on land and others can count? That coral reefs produce their own sunscreen and certain sea creatures can regenerate their entire bodies from a single piece? The ocean isn't just big and mysterious. It's strange, spectacular, and filled with facts that seem too bizarre to be true. From the physics-defying abilities of marine life to the unexpected connections between the sea and human civilization, the ocean constantly surprises us. Over the next 2 hours, we're diving deep into the most fascinating, shocking, and mind-blowing facts about the sea. These aren't mysteries or theories. These are proven, documented, verified facts that reveal just how extraordinary our ocean truly is. Let's explore what we know for certain about the greatest feature of our planet. Before we dive into specific facts, let's establish the basics. What exactly is the ocean? It seems like a simple question, but the answer reveals something surprising. Technically, Earth has one global ocean. What we call different oceans, the Pacific, Atlantic, Indian, Southern, and Arctic, are really just regions of a single, interconnected body of water. There are no walls between them, no clear boundaries. The distinction is geographical and historical, not physical. This matters because it means that anything happening in one part of the ocean affects all other parts. Pollution released off the coast of California will eventually spread worldwide. Overfishing in one region impacts fish populations everywhere. Climate change, warming one ocean basin warms them all. We truly have one global ocean. The ocean contains roughly 352 quintillion gallons of water. That's 352 followed by 18 zeros. If you tried to count to that number, saying one number per second, it would take you over 11 billion years, longer than the universe has existed. The average depth of the ocean is 12,100 feet, or about 2.3 miles. The deepest point, the Challenger Deep in the Mariana Trench, reaches 36,070 feet, nearly 7 miles down. To put that in perspective, if you could somehow drain all the water from the ocean, the Mariana Trench would be so deep that commercial jets flying at cruising altitude could fit inside it with room to spare. The ocean floor has more mountains, valleys, and plains than all the continents combined. The longest mountain range on Earth is underwater. The mid-ocean ridge system stretches over 40,000 miles, making it 10 times longer than the Andes, the longest continental mountain range. The ocean contains 94% of all life on Earth. Yes, despite covering only 71% of the surface, the ocean's volume is so vast that it supports far more living organisms than all terrestrial environments combined. A single bucket of seawater contains more organisms than there are people on Earth. Water pressure in the ocean increases by about 1 atmosphere for every 33 feet of depth. At the bottom of the Challenger Deep, the pressure exceeds 16,000 pounds per square inch. That's equivalent to having 50 jumbo jets stacked on top of you, yet life exists even there. The ocean regulates Earth's climate by absorbing and redistributing heat. Without this regulation, our planet would experience far more extreme temperature variations, making much of it uninhabitable. The ocean has absorbed over 90% of the excess heat trapped by greenhouse gases since the 1970s, buffering us from even more severe climate change. Ocean currents move enormous quantities of water around the globe. The Gulf Stream alone transports more water than all the world's rivers combined, about 100 times more. These currents are like conveyor belts, distributing heat, nutrients, and marine life across vast distances. Now that we understand the basics, Let's explore the specific facts that make the ocean so extraordinary. We'll start with something that seems impossible: ocean life that defies the laws of nature as we understand them. Evolution has produced millions of species perfectly adapted to ocean environments. But some marine creatures have abilities so extreme they seem to violate basic biological principles. These aren't mysteries, they are documented, studied phenomena that nonetheless challenge our understanding of what life can do. Let's start with immortality. The Turritopsis doanei jellyfish, commonly called the immortal jellyfish, can theoretically live forever. When injured, sick, or old, it reverts to its juvenile polyp stage and grows into an adult again. It can repeat this cycle indefinitely. Scientists have observed individual specimens doing this multiple times in laboratory conditions. The process, called transdifferentiation, involves cells transforming into different cell types, something most complex animals cannot do. A nerve cell becomes a muscle cell. Stomach tissue becomes reproductive tissue. The jellyfish essentially ages backward, then forward, then backward again, potentially forever. Why doesn't this make the species invincible? Because they can still die from predation, disease, or physical damage that kills them before they can transform. But absent those factors, they don't age to death. They've solved the biological aging problem entirely. Next, consider the mantis shrimp, which has perhaps the most powerful strike in the animal kingdom relative to its size. This colorful crustacean can punch with acceleration equivalent to a .22 caliber bullet. The strike is so fast, it boils the water around it, creating cavitation bubbles that implode with tremendous force and a flash of light. The mantis shrimp's club can break aquarium glass. It can split open clam shells instantly. If a human had the same striking power proportional to body size, we could throw a baseball into orbit. The creature has specialized spring-loaded appendages that store energy like a crossbow, then release it in less than 3 milliseconds. But the mantis shrimp's eyes might be even more impressive than its punch. They have 16 types of color receptors compared to our 3, allowing them to see colors we can't even imagine. They can perceive ultraviolet light, polarized light, and possibly even detect cancer cells by seeing the way malignant tissue polarizes light differently than healthy tissue. Researchers are studying their vision to develop better cancer detection tools. The pistol shrimp, despite being just an inch or two long, produces one of the loudest sounds in the ocean. It snaps its claw shut so rapidly that it creates a cavitation bubble. When this bubble collapses, it produces a sound reaching 210 decibels, louder than a gunshot, and generates temperatures briefly reaching nearly 8,000 degrees Fahrenheit, almost as hot as the sun's surface. The shockwave from this snap stuns or kills prey. Entire colonies of pistol shrimp create so much noise they interfere with sonar and underwater communication systems. During World War II, submarines used pistol shrimp colonies as acoustic camouflage, hiding their engine noise in the cacophony of snapping shrimp. Then there's the hagfish, which produces slime as a defense mechanism. When attacked, it secretes a small amount of protein and mucus that, upon contact with seawater, expands into several gallons of thick, fibrous slime within milliseconds. This slime clogs the gills of predatory fish, causing them to release the hagfish and retreat. The slime is so effective that researchers are studying it for military and commercial applications. It's stronger than spider silk, more expandable than any synthetic material, and completely biodegradable. A spoonful of hagfish slime proteins can create enough slime to fill a bucket. The mimic octopus can impersonate over 15 different species, including lionfish, sea snakes, stingrays, and jellyfish. It changes not just its color and texture, but its behavior and body shape, extending arms to mimic the flowing movement of sea snakes or flattening itself to look like a flounder. It assesses which predator is threatening it and transforms into something that predator fears. This requires incredible intelligence. The octopus must recognize the predator, remember which animals that predator avoids, and execute a convincing impression, all in seconds. It's cognitive problem-solving happening in real time during life-threatening situations. The archerfish can spit water with such precision that it knocks insects off branches several feet above the water's surface. But here's the remarkable part: it compensates for light refraction. When you look at an object above water from below, it appears to be in a different position than it actually is. The archerfish accounts for this optical illusion and aims where the insect really is, not where it appears to be. This requires sophisticated understanding of physics. Young archerfish learn this skill by watching older fish, suggesting cultural transmission of knowledge. They also adjust their aim based on prey size and distance, demonstrating calculation and prediction abilities. The electric eel generates up to 860 volts of electricity, enough to stun a horse. It uses this ability to navigate, communicate, and hunt. But recent research revealed something even more remarkable. Electric eels hunt in groups, coordinating their electrical discharges to create more powerful combined shocks. This is the only known case of coordinated electrical hunting. They also use electricity in sophisticated ways. Low voltage pulses for navigation, medium voltage for communication with other eels, high voltage for stunning prey. They can control the intensity, frequency, and timing of their discharges with precision. The stonefish is the most venomous fish in the world, with spines containing toxins so powerful that stepping on one causes excruciating pain, tissue death, and potentially cardiac arrest. But it also has the fastest strike of any fish. It can extend its jaws and swallow prey in less than 15 milliseconds, faster than you can blink. The leafy sea dragon looks exactly like drifting seaweed, with elaborate appendages resembling leaves. It's so well camouflaged that it barely needs to move. It has no teeth or stomach, surviving by sucking up small crustaceans through its snout like a living straw. Then there's the parrotfish, which has an unusual nighttime routine. It creates a mucus cocoon around its entire body before sleeping. This cocoon masks its scent, protecting it from nocturnal predators. In the morning, it eats its way out of the cocoon and goes about its day. Every single night, it builds a new sleeping bag from its own mucus. Parrotfish also play a crucial role in creating beaches. They eat algae that grows on coral, scraping it off with their beak-like teeth. In the process, they consume coral rock, digest the algae, and excrete fine white sand. A single parrotfish can produce over 800 pounds of sand per year. Much of the white sand on tropical beaches has passed through parrotfish digestive systems. The mimic octopus isn't the only shapeshifter. The sea cucumber has an even more extreme ability. It can liquefy its body. When threatened or when squeezing through tight spaces, it changes the stiffness of its connective tissue, essentially melting itself to flow through gaps, then solidifying again on the other side. It controls this at will, switching between solid and semi-liquid states. Some sea cucumbers also have another defense. They expel their internal organs toward predators. The sticky, toxic organs entangle the attacker while the sea cucumber escapes and regenerates everything it lost over the following weeks. The Greenland shark grows so slowly and lives so long that specimens have been found with harpoon fragments embedded in them from the 1800s. These sharks can live over 400 years, making them the longest-lived vertebrates known. They don't reach sexual maturity until around 150 years old. Sharks alive today may have been born before the United States existed as a nation. Finally, there's the boxer crab, which carries sea anemones in its claws like pom-poms. It uses these venomous anemones as weapons, waving them at threats. If it loses an anemone, it will find its lost anemone, tear it in half, and hold the two pieces until they regenerate into two complete anemones. It literally multiplies weapons. These abilities aren't supernatural. They are the result of millions of years of evolution solving specific survival challenges, but they demonstrate that the ocean has produced life forms with capabilities that seem to belong in science fiction rather than reality. And these extreme adaptations are just the beginning. The ocean's creatures don't just have unusual abilities, they live in ways that challenge our understanding of intelligence and consciousness itself. For decades, scientists believed intelligence was primarily a terrestrial phenomenon. Marine creatures, with their small brains and alien nervous systems, were thought to operate mainly on instinct. We were spectacularly wrong. The octopus has a brain structure completely different from vertebrate brains, yet demonstrates problem-solving abilities that rival many mammals. 2/3 of its neurons are in its arms, not its brain, allowing each arm to operate semi-independently. An octopus arm can solve a maze even when detached from the body. Octopuses have been observed opening child-proof containers, something many human toddlers struggle with. They can unscrew jar lids from the inside. They've learned to turn off lights in laboratories by squirting water at bulbs. They can navigate mazes, remember solutions, and apply learned strategies to new problems. One famous octopus named Otto, living in a German aquarium, repeatedly short-circuited the electrical system by shooting water at overhead lights. The staff only discovered this after multiple mysterious power outages. Otto apparently didn't like the bright lights and had figured out how to turn them off. Octopuses also use tools. They collect coconut shells, carry them around, and assemble them into protective shelters when needed. This demonstrates planning, gathering materials now for future use. They've been observed stacking rocks to block den entrances, sticking shells together with suction cups to create armor, and using jellyfish tentacles as weapons. Perhaps most remarkably, octopuses exhibit distinct personalities. Some are bold and exploratory, others cautious. Some are playful, repeatedly pushing floating objects just to watch them move. This suggests emotional complexity beyond simple stimulus-response behavior. Dolphins are famous for intelligence, but specific facts about their cognitive abilities are stunning. They have signature whistles that function as names. Each dolphin develops a unique whistle within its first year, and other dolphins use that whistle to call that specific individual. They're the only non-human animals known to use arbitrary labels for each other. Dolphins can understand syntax and grammar. In experiments, they differentiate between ball fetch hoop and hoop fetch ball, demonstrating understanding that word order changes meaning. They can follow complex instructions involving multiple objects and actions. They also pass the mirror test, recognizing themselves in reflections. When marked with non-toxic paint in a location they can only see in a mirror, they examine the mark, demonstrating self-awareness. Very few species pass this test: great apes, elephants, magpies, and dolphins. Dolphins teach their young cultural practices passed down through generations. In Shark Bay, Australia, some dolphins teach their offspring to use sea sponges as tools. They tear off sponges, wear them over their beaks like gloves, and use them to probe the seafloor for fish hiding in sharp coral. This behavior is learned, not instinctive, and is passed from mother to calf. Orcas, the largest members of the dolphin family, have even more complex cultures. Different orca populations have distinct dialects, hunting techniques, and social structures. They hunt cooperatively using sophisticated strategies. Some pods create waves to wash seals off ice floes, others herd fish into tight balls before attacking, and some have learned to flip sharks upside down to induce tonic immobility, paralyzing them. Orcas never stop learning. Grandmother orcas, past reproductive age, play crucial roles in pods by remembering where to find food during lean times and teaching hunting techniques to younger generations. They are the only mammals, besides humans and short-finned pilot whales, known to undergo menopause, allowing elder females to contribute knowledge rather than competing with their daughters for resources. Humpback whales compose songs. Males produce elaborate vocalizations lasting up to 20 minutes, repeating them for hours. Within a population, all males sing the same song, but the song gradually evolves over time, with new phrases added and old ones dropped. Whales across entire ocean basins sing the same version, suggesting cultural transmission across thousands of miles. Even more remarkably, humpback whales from different populations sometimes adopt each other's songs. Australian humpbacks have been recorded singing songs that originated with humpbacks near South America. Somehow, songs spread across populations that never physically meet. The mechanism remains unknown. Cleaner fish, tiny reef fish that eat parasites off larger fish, can recognize up to 100 individual client fish by sight. They remember which clients are regulars and which are visitors, providing better service to regulars because they'll return. They also cheat, occasionally nipping clients to eat mucus instead of just parasites. But they do this strategically, cheating more with resident clients who have no choice but to return, and providing better service to visitors who might not come back if treated poorly. This demonstrates forward thinking and strategic social manipulation in a fish with a brain the size of a grain of rice. The humble goldfish, despite its reputation for having a 3-second memory, can actually remember things for months. They can be trained to press levers for food, distinguish between different shapes and colors, and tell time. Goldfish anticipate feeding times, becoming active several minutes before scheduled feedings. They also feel pain and experience stress, contrary to popular belief. Studies measuring physiological responses show goldfish have pain receptors and stress hormones similar to other vertebrates. Manta rays, with the largest brain-to-body ratio of any fish, pass the mirror test. When marked and shown their reflections, they examine the marks, indicating self-recognition. This discovery was surprising because self-awareness was thought to require mammalian-level brain structure. Manta rays' brains are organized completely differently, yet produce similar cognitive capabilities. Sea lions can keep a beat. Research shows they can bob their heads to rhythmic music, adjusting their timing as the tempo changes. This requires predicting when the next beat will occur, a cognitive skill previously thought unique to species with vocal learning ability. Octopuses don't just use tools, they carry them while traveling, indicating planning for future use. They select materials based on their properties, choosing harder shells when more protection is needed. When presented with half a coconut shell, they'll search for another half to complete their shelter, demonstrating understanding that one half is insufficient. Cuttlefish can count. In experiments, they chose the box containing more shrimp up to quantities of 5, demonstrating numerical discrimination. They also passed a modified marshmallow test. When offered an immediate snack of less preferred food or waiting for preferred food, they waited longer when the preferred food was better, showing self-control and future planning. Groupers and moray eels hunt cooperatively, with groupers using specific head gestures to recruit eels. The grouper performs a shimmy dance in front of a moray eel's hiding place when it wants to hunt together. This is referential communication, a signal that references something else. The grouper is essentially saying, "Let's hunt together," through gesture. Even fish larvae show learning abilities. Experiments with damselfish larvae show they can learn predator recognition from watching the responses of adult fish, suggesting observational learning occurs very early in development. The chambered nautilus, often called a living fossil because it's remained virtually unchanged for millions of years, can solve complex spatial problems and remember solutions for months. Despite having a brain structure fundamentally different from vertebrates or even other cephalopods, it demonstrates sophisticated cognitive abilities. Perhaps most surprisingly, some fish can recognize human faces. Archerfish shown pictures of human faces can distinguish between them, even when faces are presented in black and white or from different angles. They can learn to shoot water at one specific face while ignoring others, demonstrating individual recognition across species. These facts reveal that intelligence evolved multiple times independently in the ocean. Octopuses, fish, and mammals have completely different evolutionary lineages and brain structures, yet all demonstrate problem-solving, learning, memory, and even social cognition. Intelligence isn't one thing that evolved once. It's a suite of cognitive tools that evolution has discovered repeatedly whenever the benefits of flexible behavior outweigh the costs of maintaining neural tissue. But intelligence isn't the only impressive feature of marine life. The physical abilities and record-breaking biology of ocean creatures are equally extraordinary. The ocean is home to animals that exist at the absolute limits of biological possibility. These record holders demonstrate just how extreme life can become when it has millions of years and vast space to evolve. The blue whale is the largest animal that has ever existed on Earth, larger than any dinosaur, larger than any ancient sea creature, larger than anything else we know of in Earth's entire history. Adults can reach 100 feet long and weigh 200 tons, equivalent to about 33 elephants or 2,000 adult humans. A blue whale's heart is the size of a small car and weighs about 400 pounds. Its arteries are wide enough that a human child could swim through them. The heart beats only 5 to 6 times per minute when diving, slowing down to conserve oxygen. When feeding, a blue whale can consume up to 16 tons of krill per day during peak feeding season. That's equivalent to eating about 40 million individual krill. They do this by lunging into krill swarms with their mouths open, taking in enormous volumes of water, then filtering it out through baleen plates while retaining the krill. A blue whale calf gains about 200 pounds every day for the first year of its life, drinking over 100 gallons of milk daily. The milk is so rich in fat, about 35 to 50%, that it has the consistency of toothpaste. The loudest animal on Earth is also a whale. Blue whales and fin whales produce calls reaching 188 decibels, audible to other whales over 1,000 miles away. These low-frequency vocalizations travel immense distances through water, potentially allowing whales across entire ocean basins to communicate. For comparison, a jet engine produces about 140 decibels. A rock concert reaches about 120 decibels. Whale calls are louder than standing next to a jet engine at takeoff. The fastest marine animal is the black marlin, which can reach speeds up to 80 miles per hour in short bursts. Sailfish come close at around 68 miles per hour. These speeds are achieved through streamlined bodies, powerful muscles, and specialized skin that reduces drag. To put this in perspective, Olympic swimmer Michael Phelps at peak performance reached about 6 miles per hour. A sailfish is over 10 times faster, and it sustains these speeds while chasing prey through three-dimensional space. The oldest known animal is a deep-sea sponge found in Antarctic waters. Using radiometric dating of its silica skeleton, scientists determined it's approximately 15,000 years old. It was alive when mammoths still walked the earth and humans were just beginning to develop agriculture. The oldest known individual animal with a confirmed age is a Greenland shark, estimated at 392 years old, though sponges and corals can live even longer. These sharks were born in the 1600s and have lived through centuries of human history. The deepest living fish ever recorded is a snailfish found at 26,722 feet in the Mariana Trench. At these depths, pressure exceeds 1,000 times atmospheric pressure at sea level. The fish is translucent, gelatinous, and appears almost ghostly. Its proteins and cellular structures have evolved to function under pressures that would crush most other creatures. The longest migration of any animal belongs to the Arctic tern, which flies from Arctic to Antarctic and back each year, a round trip of about 50,000 miles. Over a 30-year lifespan, one tern flies approximately 1.5 million miles, equivalent to flying to the moon and back 3 times. The largest eyes in the animal kingdom belong to the colossal squid, with each eye reaching up to 11 inches in diameter, about the size of a dinner plate. These massive eyes can detect light in the deep ocean where illumination is minimal, allowing the squid to spot prey and avoid predators in near-total darkness. The largest single living structure on Earth is the Great Barrier Reef, stretching over 1,400 miles along Australia's coast. It's composed of billions of tiny organisms called coral polyps. The reef is visible from space and contains more biodiversity than any other ecosystem, with over 1,500 species of fish and 400 species of coral. The longest recorded dive by any marine mammal was by a Cuvier's beaked whale that stayed underwater for 3 hours and 42 minutes. During this time, it dove to depths exceeding 9,000 feet. How it avoids decompression sickness, the bends, and manages oxygen for nearly 4 hours remains partially mysterious. The Portuguese man-o'-war has tentacles that can extend up to 165 feet, longer than the blue whale. Though often called a jellyfish, it's actually a colonial organism. Thousands of individual organisms called zooids that work together as one entity. Each zooid specializes in a different function: floating, catching prey, digestion, or reproduction. The whale shark is the largest fish in the world, reaching lengths up to 60 feet and weighing up to 20 tons. Despite their size, they are gentle filter feeders, swimming slowly with their huge mouths open to strain plankton and small fish from the water. They can live over 100 years and don't reach sexual maturity until around 25 years old. The giant Pacific octopus is the largest octopus species, with arm spans exceeding 20 feet and weights over 100 pounds. They're also remarkably intelligent, capable of opening jars, solving puzzles, and navigating complex mazes. They can squeeze through any opening larger than their beak, the only hard part of their body. The sailfish has the largest dorsal fin relative to body size of any fish. When extended, it can be nearly as tall as the fish's body length. The fin is used for herding prey, visual signaling, and possibly reducing drag during high-speed swimming. The ocean sunfish, or mola, can weigh up to 5,000 pounds, making it the heaviest bony fish. It has an unusual appearance, looking like a fish head with a tail but no body. Females can produce up to 300 million eggs at once, more than any other vertebrate. The box jellyfish has the most potent venom of any marine creature. Its toxin attacks the heart, nervous system, and skin cells simultaneously. Victims have been known to go into cardiac arrest before reaching shore. Fortunately, most stings aren't fatal, but severe stings can kill within minutes without treatment. The mantis shrimp has the fastest strike in the animal kingdom, with its club-like appendages accelerating at 10,000 times the force of gravity and reaching speeds of 50 miles per hour in water. The strike creates cavitation bubbles that implode with force rivaling a .22 caliber bullet. The stonefish is the most venomous fish, with spines containing toxins that cause excruciating pain, tissue death, and potentially heart failure. It's also nearly invisible, looking exactly like a crusty rock on the seafloor. Most stings occur when people accidentally step on them. The anglerfish holds the record for the most extreme sexual dimorphism. Females can reach over 3 feet long, while males are just a few inches. Males bite into females and fuse permanently, sharing blood systems. The male essentially becomes a permanent appendage that provides sperm on demand. The longest animal ever recorded is the bootlace worm, a type of ribbon worm that can exceed 180 feet in length, longer than the blue whale. Most of its length is elastic tissue that can stretch dramatically, but even at rest, these worms are extraordinarily long. The deadliest creature in the ocean isn't a shark or jellyfish, it's probably the mosquito. While not marine, Mosquitoes near coasts spread diseases that kill hundreds of thousands of people annually. In purely marine terms, the box jellyfish, blue-ringed octopus, and cone snail are among the most lethal. The fastest-growing organism on Earth is giant kelp, which can grow up to 2 feet per day in ideal conditions. A kelp forest can reach over 150 feet tall in a single growing season, creating massive underwater structures that provide habitat for thousands of species. These extremes aren't just interesting trivia. They represent the boundaries of what biology can achieve. Each record holder has pushed evolution to produce something unprecedented. The loudest sound, the largest body, the deepest dive, the fastest strike. And they remind us that the ocean, with its enormous volume and diverse environments, provides the space and conditions for life to reach scales and capabilities impossible on land. But size and speed aren't everything. Some of the ocean's most fascinating facts involve not individual extremes, but the complex interactions and surprising relationships between species. The ocean is filled with partnerships so specific and interdependent that removing one species would doom the other. These relationships, called symbiosis, reveal how deeply interconnected marine life has become over millions of years of coevolution. The relationship between clownfish and sea anemones is one of nature's most famous partnerships. Clownfish live among the venomous tentacles of anemones, which would kill most fish. They are protected by a special mucus coating that prevents the anemone's stinging cells from firing. In exchange for shelter, clownfish defend the anemone from predators, remove parasites, and even attract prey with their bright colors. But there's more to it. Clownfish provide nutrients to anemones through their waste products, essentially fertilizing their hosts. Without clownfish, anemones grow more slowly and are more vulnerable to predators. Cleaner wrasses run cleaning stations on coral reefs where larger fish line up to have parasites removed. Client fish signal they want cleaning by adopting specific postures and colors. The relationship is so established that predatory fish will wait in line peacefully next to their usual prey. The cleaning station represents neutral ground where normal predator-prey rules are suspended. Client fish benefit from parasite removal, which improves health and reduces disease. Cleaner wrasses get an easy meal, but surprisingly, removal of cleaner wrasses from a reef causes dramatic effects. Fish health declines, some species abandon the area, and reef diversity decreases. These tiny fish have outsized impacts on entire reef ecosystems. Remoras, also called suckerfish, attach to sharks, whales, and other large animals using a modified dorsal fin that acts like a suction cup. They get free transportation and access to leftover food from their host's meals. In return, they eat parasites off the host's skin and may clean wounds, though the benefit to the host is debated. What's remarkable is the remora's suction power. It can maintain attachment even when hosts are swimming at high speeds. The mechanism is so effective that engineers are studying it to design better underwater adhesives and attachment systems for marine equipment. Boxer crabs carry small sea anemones in their claws like pom-poms, waving them at threats to use their venom as weapons. The crab benefits from protection. The anemones benefit from being moved around the reef, accessing more food and territory than if they were stationary. If a crab loses an anemone, it will find the lost one, rip it in half, and hold both pieces until they regenerate into 2 complete anemones. Gobies and blind shrimp form one of the ocean's most unusual partnerships. The shrimp is an excellent digger but has poor vision. The goby has good vision but isn't a good excavator. Together, they share a burrow. The shrimp maintains it, and the goby acts as a lookout. The shrimp keeps an antenna touching the goby at all times. When danger approaches, the goby twitches, and both retreat into the burrow. Coral and zooxanthellae algae form a relationship so interdependent that coral cannot survive without it. The algae live inside coral tissue, producing nutrients through photosynthesis that the coral absorbs. In return, the coral provides shelter and access to sunlight. Up to 90% of the coral's energy comes from its algae partners. When water temperatures rise too high, the relationship breaks down. Coral expels the algae in a process called bleaching, losing both its color and its primary food source. Without algae, coral slowly starves. If temperatures return to normal quickly enough, algae recolonize and the coral recovers. If not, the coral dies. This is why ocean warming is so devastating to reefs. The relationship between whales and barnacles is mostly one-sided. Barnacles attach to whales for free transportation through nutrient-rich waters. A single gray whale can carry up to 1,000 pounds of barnacles. While generally considered parasitic, some researchers suggest barnacles might provide minor benefits by making the whale's skin rougher, reducing drag in certain swimming conditions, though this remains debated. Pilot fish swim alongside sharks, feeding on scraps and parasites. They're often found around sharks' gills and mouths, areas rich in parasites and debris. Sharks don't eat pilot fish, possibly because they provide cleaning services, or possibly because pilot fish are simply not worth the energy to catch. Hermit crabs and sea anemones also partner up. The crab allows anemones to attach to its shell, gaining camouflage and defense from the anemone's sting. The anemones gain mobility and access to food scraps when the crab eats. When a hermit crab moves to a larger shell, it carefully transfers its anemone partners to the new shell, demonstrating recognition of the relationship's value. Moray eels and groupers hunt together, one of the few known examples of interspecies cooperative hunting. Groupers use specific gestures to recruit moray eels. When hunting together, they are more successful than either would be alone. The grouper chases prey into crevices where the eel can follow, while the eel flushes prey out into open water where the grouper catches them. Pistol shrimp and gobies form cleaning partnerships. The shrimp maintains a burrow that both species share. The goby acts as a sentry while the shrimp digs. They communicate through touch, with the shrimp keeping physical contact with the goby. This allows the nearly blind shrimp to know when danger approaches. Oxpecker birds and large marine mammals like hippos form similar relationships. While hippos are technically freshwater animals that spend time in saltwater estuaries, the principle applies broadly. One species gets food by cleaning another, creating mutual benefit. Sea turtles visit specific cleaning stations where fish remove algae and parasites from their shells. The turtles adopt specific postures, extending their flippers to signal they want cleaning. They'll wait patiently while multiple fish work on them, and they return to the same cleaning stations repeatedly, suggesting memory and recognition of locations that provide this service. Show more 12:47 a.m. The relationship between certain shrimp and tube worms at hydrothermal vents exemplifies extreme environment partnerships. The shrimp graze on bacteria growing on the worm's tubes, keeping them clean and free of excessive bacterial buildup. The worms benefit from this maintenance, and the shrimp gain a steady food source in an environment where food is scarce. Perhaps the strangest partnership involves the pearlfish and sea cucumbers. The pearlfish lives inside the sea cucumber's body, entering and exiting through the sea cucumber's anus. The fish gains shelter and protection inside its host. The benefit to the sea cucumber is unclear, and the relationship might be closer to parasitism than true symbiosis, but the sea cucumber tolerates it nonetheless. These relationships demonstrate that survival in the ocean often depends not just on individual adaptations, but on building connections with other species. Evolution doesn't just shape organisms in isolation. It creates webs of interdependence where the success of one species becomes linked to the success of another. But symbiosis is just one type of interaction. The ocean contains relationships based on deception, manipulation, and biological warfare that are equally fascinating. Some ocean creatures survive not through cooperation, but through elaborate tricks and deceptions that rival anything in human spy craft. The mimic octopus we mentioned earlier doesn't just change appearance randomly. It specifically impersonates the animals its current predator fears most. If approached by a damselfish, which fears sea snakes, the octopus will elongate its body and wave two arms in opposite directions to mimic a sea snake. If approached by a different predator that fears lionfish, it transforms into a lionfish by spreading its arms and swimming differently. The frogfish uses deception to hunt. It has a modified dorsal spine that resembles a small fish or worm, which it wiggles enticingly above its mouth. When prey approaches to investigate what looks like an easy meal, the frogfish strikes with one of the fastest attacks in the animal kingdom, swallowing the prey whole in just 6 milliseconds. The stonefish takes camouflage to an extreme. It looks exactly like an algae-covered rock, complete with irregular texture and coloration. It can remain motionless for weeks, waiting for prey to swim within striking distance. Even humans walking carefully through tide pools often fail to spot stonefish until it's too late. The Indonesian mimic octopus takes deception even further. When hunting, it buries itself in sand with only its eyes exposed, then extends two arms to resemble the breathing siphons of a harmless clam. Small fish approach what looks like a safe hiding spot and are suddenly engulfed by the octopus's remaining 6 arms. The Atlantic wolffish has antifreeze proteins in its blood that prevent ice crystals from forming in freezing Arctic waters. But here's the deceptive part. It looks terrifying, with massive teeth and a fierce face, leading most predators to avoid it. In reality, it's relatively docile and poses little threat to anything it doesn't intend to eat. The cookie-cutter shark uses bioluminescence as a lure. Its entire underside glows except for a dark collar near its throat. From below, it blends with surface light, but that dark collar looks like a small fish to predators who attack from below. When a larger predator tries to eat what it thinks is a small fish, the cookie-cutter shark spins and takes a circular plug of flesh from the attacker with its specialized teeth. The stoplight lucidjaw fish has evolved red bioluminescence, which is extremely rare. Most deep-sea creatures cannot see red light. The lucidjaw uses this to illuminate prey with a beam of light that, to the prey, is invisible. It hunts with stealth lighting, seeing its prey while remaining unseen. The warty frogfish doesn't just use a lure. It walks across the seafloor on modified pectoral fins that look like tiny legs, stalking prey while perfectly camouflaged. When close enough, its lure wiggles enticingly. It combines ambush predation with active hunting in a way few other fish do. The humpback anglerfish female uses bioluminescent lures to attract prey in the deep ocean, but males use deception of a different kind. They are born with functional digestive systems and eyes, allowing them to hunt. But upon finding a female, they bite her and release enzymes that fuse their tissues together. Over time, they lose their eyes, fins, and internal organs, becoming a parasitic appendage that exists only to provide sperm. It's reproductive deception taken to a biological extreme. The plainfin midshipman fish creates humming sounds that resonate through boat hulls, leading people to believe their boats are malfunctioning. The sound is actually males calling for mates, but the deception is unintentional. Entire houseboats have been investigated for mechanical problems that turned out to be fish. The decorator crab covers itself with bits of sponge, algae, and small animals, creating living camouflage, but it's selective about what it chooses. It picks items that match its specific environment and will change its decorations when moved to different habitats. This demonstrates not just camouflage, but environmental awareness and decision-making about what constitutes effective disguise. The false cleanerfish looks nearly identical to the cleaner wrasse, even mimicking its swimming behavior. Other fish approach expecting parasite removal, but the false cleaner instead bites chunks out of them and flees. It's mimicry used for predation rather than protection, and it works because client fish have been conditioned to trust cleaner fish. The leafy sea dragon doesn't just look like seaweed. It sways with ocean currents in exactly the same rhythm as real seaweed, matching both appearance and movement to its disguise. It's biomimicry involving behavior as well as appearance. The ghost pipefish camouflages itself among sea urchin spines, matching their color and striping pattern. It hovers vertically with its snout down, positioned between spines where it's nearly invisible. It even sways slightly to match the urchin's movement. The blue-ringed octopus uses warning coloration as honest signaling rather than deception. Its bright blue rings are a truthful advertisement. I am deadly, stay away. Most creatures that see those rings flee, which benefits both parties. The octopus avoids conflict, and the other animal avoids lethal venom. The corallimorph is not coral, but looks exactly like it. It's actually more closely related to anemones. It deceives not predators or prey, but scientists who must look carefully to distinguish it from true coral. This suggests that mimicking coral provides protection even from organisms that don't eat coral, simply because coral dominates the environment. These deceptions aren't conscious lies. They're evolutionary solutions where appearing to be something else provides survival advantages. But the sophistication of these deceptions, the specificity of the mimicry, and the behavioral components involved demonstrate that evolution can produce remarkably complex survival strategies. And these individual organisms, whether cooperating or deceiving, are just the visible part of ocean life. Beneath them exists an entire world of creatures too small to see, yet vast in number and critical to everything that lives in the sea. When we think of ocean life, we picture fish, whales, and coral, but the real foundation of marine ecosystems is invisible. Microorganisms too small to see with the naked eye outnumber all visible sea life by factors so vast they are difficult to comprehend. A single milliliter of seawater, about 20 drops, contains approximately 1 million bacteria and 10 million viruses. A liter of seawater contains more microorganisms than there are people on Earth. The ocean contains roughly 1 nonillion microorganisms. That's 1 followed by 30 zeros, more individual organisms than stars in the observable universe. These aren't insignificant. They are the foundation of ocean food webs and primary drivers of global nutrient cycles. Phytoplankton, microscopic photosynthetic organisms drifting in surface waters, produce between 50 and 85% of Earth's oxygen. Every second breath you take comes from phytoplankton. They've been producing oxygen for billions of years, creating the breathable atmosphere that allowed complex life, including humans, to evolve. There are thousands of species of phytoplankton. Diatoms have beautiful silica shells in geometric patterns. Dinoflagellates can move with whip-like flagella, and some produce bioluminescence, creating the glowing blue waves sometimes seen at night. Cyanobacteria, technically bacteria rather than plankton, were Earth's first oxygen producers and still contribute significantly to oxygen production today. Phytoplankton populations fluctuate seasonally and geographically. Satellite images show massive phytoplankton blooms spanning hundreds of miles, turning ocean surfaces green or turquoise. These blooms occur when conditions are right: sufficient sunlight, nutrients, and temperature. They form the base of the food chain, feeding zooplankton, which feeds small fish, which feed larger fish, which feed apex predators. Zooplankton are tiny animals drifting in ocean currents. They include baby versions of larger animals like crabs, fish larvae, and jellyfish, plus animals that remain microscopic throughout life. Copepods, tiny crustaceans about the size of a grain of rice, may be the most abundant animals on Earth by number. They eat phytoplankton and are eaten by nearly everything else. They're the critical link between primary producers and the rest of the food web. Krill, small shrimp-like crustaceans, exist in swarms so dense they color the water pink. A single swarm can contain millions of individuals. They feed primarily on phytoplankton and are the main food source for baleen whales, seals, penguins, and many fish species. Antarctic krill alone have an estimated total biomass of about 500 million tons, one of the highest of any animal species. Marine bacteria cycle nutrients throughout the ocean. When organisms die, bacteria decompose them, releasing nutrients back into the water where phytoplankton can use them. Without bacterial decomposition, nutrients would sink to the ocean floor and become locked away, eventually depleting surface waters and collapsing food webs. Some bacteria form symbiotic relationships with animals. The Hawaiian bobtail squid has a special light organ containing bioluminescent bacteria. The bacteria glow, and the squid controls how much light escapes, using it for counter-illumination to avoid casting shadows that would reveal it to predators below. The squid provides the bacteria with nutrients and a safe home. The bacteria provide camouflage lighting. Bacteria at hydrothermal vents form the base of entire ecosystems that don't rely on sunlight. These chemosynthetic bacteria extract energy from chemicals in the superheated water, primarily hydrogen sulfide. They produce organic compounds that feed tube worms, clams, and other vent organisms. It's life based on Earth's internal heat rather than solar energy. Marine viruses infect and kill bacteria, regulating bacterial populations and releasing nutrients when bacterial cells burst. Viruses transfer genes between bacteria, facilitating horizontal gene transfer that drives bacterial evolution. Some scientists estimate that viruses cause a trillion infections in the ocean every second, cycling enormous amounts of carbon and nutrients. Marine fungi, less studied than bacteria, decompose organic matter and form symbiotic relationships. Some fungi partner with algae to create lichens that colonize rocky shores. Others infect and kill harmful algae blooms, naturally controlling populations that might otherwise damage ecosystems. Archaea, single-celled organisms similar to bacteria but genetically distinct, thrive in extreme ocean environments. They're abundant in deep cold waters and around hydrothermal vents. Some archaea oxidize ammonia, contributing to nitrogen cycling. Others produce methane in ocean sediments. The microbial loop describes how dissolved organic matter, too small for most animals to eat, is consumed by bacteria, which are then eaten by larger organisms. This loop recycles nutrients that would otherwise be lost and makes energy available to food webs that would otherwise be inaccessible. Prochlorococcus is possibly the most abundant photosynthetic organism on Earth. This tiny cyanobacterium produces roughly 20% of the oxygen in Earth's atmosphere. Despite its importance, it wasn't discovered until 1988. There are likely billions of trillions of individual Prochlorococcus cells in the ocean at any moment. Marine snow is not snow, but a continuous shower of organic matter, dead organisms, feces, and mucus drifting down from surface waters to the deep sea. It falls slowly, taking weeks or months to reach the bottom. Marine snow is the primary food source for deep-sea organisms and transports carbon from surface waters to the ocean floor, sequestering it for centuries or millennia. Some bacteria produce toxins that accumulate in shellfish, causing harmful algal blooms. When humans eat contaminated shellfish, they can experience paralytic shellfish poisoning, which can be fatal. The bacteria aren't trying to harm humans. They produce toxins as metabolic byproducts or defensive chemicals. Humans are collateral damage. Bioluminescent bacteria are responsible for most bioluminescence in the ocean. They live freely in water or inside light organs of fish and squid. The chemical reaction that produces light is called luciferin-luciferase reaction, where luciferin is oxidized by the enzyme luciferase, producing light with minimal heat. Marine microorganisms are being studied for biotechnology applications. Bacteria that produce antifreeze proteins could help preserve organs for transplant. Bacteria that digest plastic could help clean up pollution. Bacteria that produce unique enzymes could create new pharmaceuticals. The ocean's microbial diversity represents a vast, mostly untapped resource for medical and industrial applications. The ocean's invisible life isn't just interesting biology, it's the machinery that makes the ocean work. Without microorganisms, nutrients wouldn't cycle, organic matter wouldn't decompose, oxygen wouldn't be produced, and food webs would collapse. Every visible ocean creature depends on invisible organisms they'll never see. These microscopic organisms don't just support ocean life. They drive chemistry that affects the entire planet, including properties of seawater itself that make the ocean unique. Seawater isn't just water with salt added. It's a complex chemical solution with properties that determine ocean circulation, support marine life, and influence global climate. Understanding seawater chemistry reveals why the ocean behaves the way it does. Seawater is approximately 96.5% water and 3.5% dissolved salts. That 3.5%, called salinity, contains primarily sodium chloride, table salt, but also includes magnesium, calcium, potassium, and dozens of other elements. Every naturally occurring element on the periodic table exists in seawater, though many in trace amounts. If you evaporated all the ocean's water, the remaining salt would form a layer 500 feet thick, covering the entire planet. That's enough salt to bury a 45-story building. Salinity varies geographically. The Dead Sea and Red Sea have higher salinity due to high evaporation and low freshwater input. The Baltic Sea has lower salinity due to river inflow and low evaporation. Open ocean salinity is relatively stable at about 35 parts per thousand. Salt makes seawater denser than freshwater. This density difference drives ocean circulation. Salty, cold water is denser and sinks. Less salty, warm water is less dense and floats. This creates vertical movement called thermohaline circulation, which distributes heat and nutrients throughout ocean basins. The ocean is slightly alkaline with a pH around 8.1. But increasing atmospheric carbon dioxide is making seawater more acidic, a process called ocean acidification. The ocean has absorbed about 30% of human-produced carbon dioxide since the Industrial Revolution. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering pH. Ocean acidification threatens marine life, especially organisms that build shells or skeletons from calcium carbonate. As seawater becomes more acidic, calcium carbonate dissolves more easily. Corals, shellfish, and many plankton species struggle to build and maintain their structures. If acidification continues, some organisms might be unable to form shells at all. Seawater freezes at about 28.4 degrees Fahrenheit, lower than freshwater's 32 degrees. The salt interferes with ice crystal formation. However, when seawater does freeze, it excludes most salt, forming relatively fresh ice. The rejected salt concentrates in surrounding water, making it even denser and causing it to sink. The ocean contains dissolved gases, including oxygen and carbon dioxide. Surface waters in contact with air are well oxygenated. Deep waters receive oxygen from cold, sinking surface water at polar regions. However, some ocean regions called oxygen minimum zones have very low oxygen levels due to bacterial decomposition consuming oxygen faster than it can be replenished. Some ocean zones are completely anoxic, lacking oxygen entirely. The Black Sea below about 600 feet is anoxic due to stable layering that prevents oxygen-rich surface water from mixing with deep water. Only specialized anaerobic bacteria can survive there. The ocean contains vast amounts of dissolved organic matter, estimated at about the same mass as all carbon in Earth's atmosphere. This organic matter comes from dead organisms, waste products, and secretions from living organisms. It's an important energy source for bacteria and contributes to nutrient cycling. Temperature and salinity together determine seawater density, which drives ocean circulation. Warm water expands and becomes less dense. Cold water contracts and becomes denser. Very cold, very salty water in polar regions is the densest seawater and sinks to the ocean floor, driving deep ocean currents that circulate globally over centuries. The ocean absorbs enormous amounts of heat from the sun. Water has high heat capacity, meaning it takes a lot of energy to change its temperature. This property makes the ocean an effective climate regulator. Coastal areas have milder climates than inland areas at the same latitude because nearby ocean water moderates temperature swings. Seawater is electrically conductive due to dissolved ions. This conductivity can be measured to determine salinity. It also allows some fish to use electrical fields for navigation and communication. The ocean contains gold, about 20 million tons of it, dissolved at concentrations of about 13 billionths of a gram per liter. Extracting it would cost far more than the gold's value, so it remains dissolved. But knowing it's there reminds us that oceans contain essentially every element, given enough volume. The ocean contains methane trapped in ice-like structures called methane hydrates on continental slopes and seafloor sediments. There may be more energy stored in methane hydrates than all other fossil fuels combined. However, extracting it is technically challenging, and releasing it could worsen climate change since methane is a potent greenhouse gas. Seawater pressure increases dramatically with depth. At the ocean's average depth of about 12,000 feet, pressure is approximately 380 times atmospheric pressure. At the deepest point in the Mariana Trench, pressure exceeds 1,000 atmospheres. This pressure crushes air-filled spaces but doesn't crush water or organisms made mostly of water, since water is nearly incompressible. The ocean's chemistry isn't static. Human activities are changing it through pollution, acidification, warming, and nutrient runoff. Understanding seawater chemistry helps scientists predict and mitigate these changes, but seawater itself is just one component of ocean dynamics. The water moves constantly, driven by forces that shape climate and distribute life. The ocean never stops moving. Currents, waves, and tides distribute heat, nutrients, and organisms across the planet. These movements connect distant ocean regions and profoundly influence global climate and weather patterns. Ocean currents are like rivers flowing through the sea. Surface currents are primarily driven by wind. The trade winds near the equator push water westward. Westerlies at higher latitudes push water eastward. The Coriolis effect, caused by Earth's rotation, deflects currents to the right in the northern hemisphere and left in the southern hemisphere, creating circular patterns called gyres. There are 5 major ocean gyres: North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian Ocean. These gyres circulate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. They concentrate floating debris, creating garbage patches where plastic and other trash accumulate. The Great Pacific Garbage Patch is not a solid island of trash, but a diffuse area with higher than normal concentrations of plastic debris. It covers an area roughly twice the size of Texas. Most plastic is broken into tiny fragments called microplastics. These microplastics are eaten by marine animals, potentially entering food webs and eventually human food sources. The Gulf Stream is one of the strongest and most significant ocean currents. It transports warm water from the Gulf of Mexico along the eastern United States and across the Atlantic toward Europe. It moves about 4 billion cubic feet of water per second, roughly 100 times the flow of all rivers on Earth combined. The Gulf Stream moderates climate, making northern Europe much warmer than it would otherwise be at that latitude. If the Gulf Stream weakens or stops, which some climate models suggest could happen with continued Arctic ice melt, Europe could experience dramatically colder winters. Evidence suggests this has happened in Earth's past, triggering rapid regional cooling. Thermohaline circulation, also called the global conveyor belt, moves water through all ocean basins over roughly 1,000 years. Cold, salty water sinks in the North Atlantic and Antarctic, flowing deep along the ocean floor. It eventually rises in the Indian and Pacific Oceans, warms, and returns to the Atlantic at the surface. This circulation distributes heat, carbon, and nutrients globally. Upwelling occurs when winds push surface water away from coastlines, causing deeper, colder, nutrient-rich water to rise and replace it. Upwelling zones are among the most productive ocean regions, supporting rich fisheries. The west coasts of continents, including California, Peru, and West Africa, experience significant upwelling. Downwelling occurs when surface water converges and sinks. It transports oxygen-rich surface water to depth, supplying deep-sea organisms with oxygen. Without downwelling, deep ocean oxygen would gradually be consumed by bacterial decomposition, creating anoxic conditions. Ocean waves are mostly created by wind transferring energy to water. The size of waves depends on wind speed, duration, and fetch, the distance over which wind blows. Storm systems can generate waves exceeding 60 feet. The largest wave ever measured by scientific instruments was 95 feet tall, recorded in the North Atlantic during a storm. But there's another type of wave far larger. Internal waves occur beneath the ocean surface at the boundary between water layers of different densities. These waves can exceed 600 feet tall, dwarfing surface waves. They move slowly and aren't visible from the surface, but they transport enormous amounts of water and energy. Submarines must navigate carefully to avoid internal waves, which can cause sudden depth changes. Rogue waves are unusually large, steep waves that appear suddenly in open ocean. They can exceed 80 feet and pose serious danger to ships. For centuries, sailors reported rogue waves, but scientists dismissed them as exaggerations. Then in 1995, instruments on an oil platform measured a rogue wave 84 feet tall, confirming they exist. We now know rogue waves form when several wave systems converge, their energy adding together to create one massive wave. Tsunamis are not wind-driven, but are caused by underwater earthquakes, landslides, or volcanic eruptions. They move at speeds exceeding 500 miles per hour in deep ocean, but slow dramatically as they approach shore, piling up into devastating walls of water. The 2004 Indian Ocean tsunami killed over 230,000 people, one of the deadliest natural disasters in recorded history. Tides are caused primarily by the moon's gravitational pull, with the sun contributing about half as much. The moon pulls ocean water toward it, creating a bulge. On the opposite side of Earth, water also bulges outward due to inertia. As Earth rotates through these bulges, most coastlines experience 2 high tides and 2 low tides per day. Tidal range, the difference between high and low tide, varies geographically. The Bay of Fundy in Canada has the highest tides in the world, reaching over 50 feet. In contrast, some enclosed seas have negligible tides. Tidal range also varies with lunar phases. During full and new moons, when the sun and moon align, tides are higher than average, called spring tides. During quarter moons, tides are lower, called neap tides. Tidal currents flow as water moves between high and low tide. In narrow channels or bays, these currents can be extremely strong, creating dangerous conditions for navigation. The Old Sow Whirlpool off the coast of New Brunswick is caused by tidal currents and can reach 75 feet in diameter. Some ocean locations experience tidal bores, where incoming tide forms a wave that travels up rivers. The Kayantang River in China has a tidal bore reaching up to 30 feet, attracting surfers and tourists. Ocean circulation influences weather and climate. El Niño and La Niña are climate patterns caused by changes in Pacific Ocean temperatures and circulation. During El Niño, warm water spreads eastward across the Pacific, altering weather patterns globally. It typically brings drought to Australia and Indonesia while increasing rainfall in South America. La Niña has roughly opposite effects. These patterns affect fisheries, agriculture, and extreme weather events worldwide. Predicting El Niño and La Niña helps governments and industries prepare for likely impacts. Ocean movement also distributes marine organisms. Many species have larval stages that drift with currents, sometimes traveling thousands of miles before settling. This dispersal connects populations across vast distances and allows species to colonize new areas. Some species like sea turtles and salmon use ocean currents to navigate during migrations. The continuous movement of ocean water means the ocean is never truly still. Even in the deepest trenches, currents flow slowly along the bottom. This movement is essential for distributing oxygen, nutrients, and heat. Without ocean circulation, the ocean would stratify, with warm, low-oxygen surface water above cold, stagnant deep water. Life would be far less abundant and diverse. Ocean dynamics are complex, involving interactions between temperature, salinity, wind, Earth's rotation, and underwater topography. Scientists use sophisticated computer models to simulate ocean circulation and predict changes. Understanding these movements helps us forecast climate, manage fisheries, and predict how the ocean will respond to human influences. And humans have influenced the ocean profoundly. Our relationship with the sea extends back to our earliest ancestors and continues to shape both human civilization and ocean ecosystems. Humans have always been drawn to the ocean. Coastal settlements date back tens of thousands of years. The sea provided food, enabled trade, inspired exploration, and shaped cultures. Our relationship with the ocean is deep, complex, and increasingly consequential. Early humans used the ocean primarily for food. Shellfish middens, piles of discarded shells, mark ancient coastal settlements worldwide. Fish bones in archaeological sites show humans were fishing at least 40,000 years ago. Coastal resources provided reliable nutrition that helped early human populations survive and expand. Ancient civilizations developed sophisticated maritime cultures. Polynesians navigated thousands of miles of open ocean using stars, wave patterns, and bird behavior, colonizing islands across the Pacific. Vikings crossed the North Atlantic to reach North America centuries before Columbus. Chinese sailors explored throughout Southeast Asia and beyond. The ocean was a highway connecting distant lands. Maritime trade shaped human history. The Silk Road included maritime routes connecting Asia, the Middle East, and Europe. Spices, silk, and other valuable goods traveled by ship, creating wealth and cultural exchange. Control of sea routes meant power. The rise and fall of maritime empires, from ancient Athens to Venice to Britain, depended on naval strength. The age of exploration in the 15th and 16th centuries was driven by desire to find sea routes to Asia. European explorers mapped coastlines, enabling colonization and trade that transformed the world. Ferdinand Magellan's expedition circumnavigated the globe, proving Earth's roundness and revealing the ocean's vast extent. The Industrial Revolution changed our relationship with the sea. Steam-powered ships enabled faster, more reliable ocean travel. Iron and steel hulls created larger, stronger vessels. Industrialized fishing with mechanized trawlers dramatically increased catch volumes. By the 20th century, humans were extracting resources from the ocean at unprecedented scales. The ocean became a dumping ground for waste. For decades, cities dumped raw sewage and garbage directly into coastal waters. Industries released chemicals and heavy metals. Ships disposed of trash overboard. Until the 1970s, some countries dumped radioactive waste in the ocean, believing the vast volume would dilute it harmlessly. We now know ocean pollution causes serious harm. Plastic pollution has contaminated every ocean region, from surface waters to the deepest trenches. Marine animals ingest plastic, mistaking it for food. Plastic blocks digestive systems, causing starvation. Chemicals in plastic disrupt hormones and reproduction. Microplastics have been found in fish, shellfish, sea salt, and even human bodies. Chemical pollution damages marine ecosystems. Agricultural runoff carries fertilizers into coastal waters, causing algae blooms that deplete oxygen and create dead zones where most marine life cannot survive. The Gulf of Mexico has a seasonal dead zone larger than New Jersey caused by nutrient pollution from the Mississippi River. Heavy metal pollution from mining and industrial processes contaminates seafood. Mercury, particularly concerning because it bioaccumulates, moving up food chains and concentrating in predators. Large predatory fish like tuna and swordfish contain mercury levels that can be dangerous, especially for pregnant women and children. Oil spills damage marine environments. The Deepwater Horizon spill in 2010 released over 200 million gallons of oil into the Gulf of Mexico, killing wildlife, contaminating wetlands, and harming fisheries. The Exxon Valdez spill in Alaska in 1989 devastated Prince William Sound's ecosystem. Recovery from major oil spills takes decades. Overfishing has depleted fish populations worldwide. Industrial fishing fleets use technologies that find and catch fish with ruthless efficiency. Bottom trawling drags weighted nets across the seafloor, destroying habitats. Longlines with thousands of baited hooks catch not just target species, but also sea turtles, seabirds, and sharks. Drift nets, sometimes called walls of death, catch everything in their path. Many fish populations have collapsed. Atlantic cod, once so abundant that reports described walking across their backs, is now commercially extinct in many regions. Bluefin tuna populations have declined by over 90%. Sharks, slow to reproduce, are particularly vulnerable, with some populations reduced by 99%. The tragedy is that overfishing hurts fishermen too. Depleted fish populations mean reduced catches and economic hardship for fishing communities. Short-term profit has led to long-term losses for everyone. Climate change is warming the ocean, altering ecosystems, and threatening marine life. Coral reefs are bleaching and dying. Fish populations are shifting toward cooler waters, disrupting established fisheries. Sea ice is shrinking, threatening species like polar bears and seals that depend on it. Rising sea levels from thermal expansion and melting ice threaten coastal communities. Low-lying island nations face existential threats. Major cities including Miami, New York, Shanghai, and Jakarta are vulnerable to flooding. By 2100, hundreds of millions of people may be displaced by rising seas. Ocean acidification, caused by absorbed carbon dioxide, is changing ocean chemistry. It threatens shell-forming organisms with cascading effects throughout food webs. If acidification continues unchecked, entire ecosystems could collapse, yet the ocean is resilient. Given time and reduced pressure, ecosystems can recover. Protected areas allow fish populations to rebuild. Pollution regulations have cleaned some waterways. International cooperation has reduced some threats. Understanding our impact is the first step toward changing our relationship with the ocean. Humans depend on the ocean for food, climate regulation, oxygen production, and countless other services. Protecting the ocean isn't just about saving marine life. It's about preserving systems that human civilization depends on. And there are reasons for hope. Conservation efforts have achieved remarkable successes, demonstrating that positive change is possible. Despite daunting challenges, conservation successes show that protecting the ocean is possible when communities, governments, and scientists work together. The recovery of humpback whale populations is a conservation triumph. Commercial whaling nearly drove humpbacks to extinction, with populations reduced by over 95%. The International Whaling Commission implemented a moratorium on commercial whaling in 1986. Since then, humpback populations have rebounded dramatically. Some populations have recovered to near pre-whaling numbers, a testament to what protection can achieve. Gray whales tell a similar story. The eastern Pacific gray whale population was severely depleted by hunting, but has recovered fully after decades of protection. In 1994, it was removed from the endangered species list, one of the first marine mammals to achieve this milestone. Sea turtles were once harvested extensively for meat, eggs, and shells. Green sea turtles, hawksbill turtles, and loggerhead turtles faced severe population declines. Conservation efforts, including beach protection, fishing gear modifications, and international treaties, have helped populations stabilize and begin recovering. Some beaches that once saw 0 turtle nests now see hundreds annually. The California sea otter was hunted to near extinction for its fur. By the early 1900s, fewer than 50 remained. With protection, the population has grown to over 3,000. Sea otters are keystone species, maintaining kelp forests by eating sea urchins. Their recovery has restored ecosystem balance along California's coast. Marine Protected Areas (MPAs) have proven effective at restoring fish populations and biodiversity. The Great Barrier Reef Marine Park, established in 1975, protects the world's largest coral reef system. While the reef faces challenges from climate change and pollution, the park has helped reduce direct human impacts and maintain healthier conditions than would exist without protection. The Papahanaumokuakea Marine National Monument in Hawaii protects 583,000 square miles of ocean, one of the largest protected areas on Earth. Fish populations inside the monument are significantly larger and more diverse than in nearby fished areas. The monument demonstrates that large-scale protection works. The Monterey Bay National Marine Sanctuary in California helped restore populations of sea otters, whales, and other species. The sanctuary's education programs have raised awareness about marine conservation, influencing millions of visitors. Community-based conservation in the Philippines has restored coral reefs and fish populations through local management of marine resources. Villages establish and enforce fishing regulations, protect breeding areas, and monitor ecosystems. When local people have authority over resources and see direct benefits from conservation, they become effective stewards. The recovery of elephant seal populations is remarkable. These massive seals were hunted to the brink of extinction in the 1890s, with possibly fewer than 100 individuals remaining. With protection, the population has rebounded to over 200,000. Elephant seals now crowd beaches along the California coast, a dramatic conservation success. Seafood certification programs like the Marine Stewardship Council help consumers choose sustainably caught fish. By creating market incentives for sustainable fishing, these programs encourage better practices. Fisheries pursuing certification must demonstrate they are not overfishing, minimizing ecosystem damage, and managing effectively. Technological innovations help reduce fishing's environmental impact. Turtle excluder devices on shrimp nets allow turtles to escape, dramatically reducing turtle deaths. Circle hooks reduce seabird bycatch in longline fisheries. Fish aggregating devices with better designs reduce bycatch of juvenile tuna. International cooperation has banned some of the most destructive fishing practices. The United Nations has prohibited large-scale drift nets in international waters. While enforcement remains challenging, the ban has reduced drift net use and saved countless marine animals. Coral reef restoration efforts are showing promise. Scientists grow coral fragments in nurseries, then transplant them to damaged reefs. Some restored reefs are recovering, with corals growing and fish populations increasing. While restoration can't replace prevention, it offers hope that damaged ecosystems can be repaired. Genetic rescue is being studied for endangered species. Scientists can preserve genetic material from dying populations, potentially using it to increase genetic diversity in future generations. This technology is controversial and expensive, but it could help prevent extinctions. Education and awareness have increased dramatically. Documentaries and social media expose millions of people to ocean issues. Youth activists are demanding action on climate change and pollution. Public pressure has forced governments and corporations to implement better policies. Plastic bag bans, implemented in many cities and countries, reduce ocean plastic pollution. These bans face resistance, but demonstrate that policy changes can meaningfully address pollution. The recovery of Atlantic striped bass shows that fishing regulations work. Strict catch limits imposed when the population crashed allowed the population to rebuild. The fishery is now sustainable and economically valuable. Whale watching has become an economic alternative to whaling. Communities that once hunted whales now earn income from tourists who pay to see them alive. This economic shift creates incentives for conservation and demonstrates that intact ecosystems have economic value. The Antarctic Treaty and subsequent protocols protect Antarctic waters from exploitation. The agreement prohibits mineral extraction and regulates fishing, preserving one of Earth's last pristine ocean regions. Oyster restoration in Chesapeake Bay is improving water quality. Oysters filter water, removing excess nutrients and sediment. Restored oyster reefs are helping clean the bay and providing habitat for other species. These successes share common features: legal protection, enforcement, scientific monitoring, community involvement, and long-term commitment. Conservation works when people recognize that protecting the ocean serves their interests. The ocean faces serious threats, but it's not too late. Every action to reduce pollution, protect habitats, limit overfishing, and address climate change helps. The successes we've achieved demonstrate that we have the knowledge and tools to protect the ocean. What's needed is collective will to use them. The ocean has given humanity everything: the water we drink, the air we breathe, the climate that makes our planet habitable, food for billions, transportation routes, cultural inspiration, and scientific wonder. In return, we have a responsibility to protect it. Our understanding of the ocean remains incomplete. We've explored less than 5% of the ocean floor. New species are discovered constantly. Each research expedition reveals surprises. The ocean continues to teach us about biology, chemistry, physics, and Earth's history. The ocean reminds us that we live on a water planet, that the boundaries we draw between ocean basins are artificial, that actions in one place affect conditions everywhere, and that our fate is linked to the ocean's health. The ocean doesn't need humanity to exist. But humanity absolutely needs a healthy ocean to survive. Everything we've discussed, every fact we've explored, is real, documented, and verified. The immortal jellyfish, the mantis shrimp's punch, the intelligence of octopuses, the size of blue whales, the intricacies of symbiosis, the vast numbers of microorganisms, the complex chemistry of seawater, the power of ocean currents, the history of human relationships with the sea, and the successes of conservation efforts are all established knowledge. The ocean is not mystical or magical. It's physical, chemical, and biological, yet its reality is more extraordinary than any fiction. The facts themselves inspire wonder, respect, and appreciation for the greatest feature of our planet. We stand at a pivotal moment. The decisions we make today about pollution, fishing, climate change, and conservation will determine the ocean's future, and by extension, humanity's future. We can choose to protect the ocean, allowing it to continue providing the services that all life depends on, or we can continue degrading it until critical systems collapse. The facts tell us what's possible. The ocean can recover if given the chance. Species can rebound. Ecosystems can restore themselves. Water can cleanse itself if we stop poisoning it. The ocean's resilience is remarkable, but resilience has limits. We must act before those limits are exceeded. Each of us can make choices that help the ocean. Reduce plastic use, choose sustainable seafood. Support conservation organizations. Advocate for policies that protect marine environments. Educate others about ocean issues. Even small actions, when multiplied by millions of people, create significant positive change. The ocean has been here for billions of years. It covered Earth long before humans existed. It will likely remain long after we are gone. The question is not whether the ocean will survive, but whether we will maintain an ocean that can support human civilization and the incredible diversity of life that currently exists. The facts we've explored reveal an ocean that is vast yet vulnerable, powerful yet delicate, alien yet familiar. It is home to life forms that challenge our understanding of biology. It drives systems that regulate our climate. It provides resources that billions of people depend on. It inspires art, literature, and science. It holds secrets we're only beginning to uncover. The more we learn about the ocean, the more we realize how much we don't know. But we know enough to understand that protecting it is essential. We know enough to recognize that our actions matter. We know enough to make better choices. The ocean's story is not finished. New chapters are being written every day through the interactions of countless organisms, the movement of currents, the cycling of nutrients, and the impacts of human activity. We are part of this story, not separate from it. What happens to the ocean happens to us. The facts we've shared today are just a glimpse into the ocean's complexity. Every fact leads to more questions. Every answer reveals new mysteries. The ocean rewards curiosity and careful study. It offers endless opportunities for discovery. For 2 hours, we've explored what we know about the sea. We've learned about creatures that seem impossible, intelligence that rivals our own, extremes that push the boundaries of life, partnerships that demonstrate cooperation, invisible organisms that drive global systems, chemistry that shapes our planet, movements that distribute energy and life. Human impacts both destructive and protective, and successes that provide hope. The ocean deserves our attention, respect, and protection. It has supported life on Earth for eons. It supports your life right now, providing oxygen, regulating climate, and supplying resources. The ocean is not somewhere else. It's here, connected to every place through atmospheric and hydrological cycles. When you see the ocean, whether in person or in images, remember the facts we've discussed. Remember the immortal jellyfish, the cooperative hunting of dolphins, the enormous heart of the blue whale, the partnership between clownfish and anemones, the trillion viral infections happening each second, the pH balance that makes life possible. The Gulf Stream carrying warmth across an ocean, the millennia of human dependence on the sea, and the whales that recovered from near extinction. The ocean is not just big and wet. It's intricate, astonishing, and essential. It contains more wonders than we've described, more species than we've counted, more processes than we understand. But what we do know is extraordinary. This is the ocean. These are the facts. This is the blue planet we call home. The greatest feature of Earth is not land, but water. Not continents, but the sea. Not what we've built, but what nature has created over billions of years of evolution and geological processes. The ocean is our life support system, our historical highway, our largest ecosystem, our climate regulator, our oxygen supplier, and our final frontier for exploration. Every second breath you take comes from the ocean. Every drop of rain began as ocean water evaporated into clouds. Every creature on land descended from ancestors that evolved in the sea. We are connected to the ocean at the most fundamental levels of biology and chemistry. The facts we've shared are gifts from researchers, scientists, and explorers who devoted their lives to understanding the ocean. They dove deep, sailed far, studied carefully, and reported honestly about what they found. Their work reveals truths more incredible than myths, facts stranger than fiction, and realities more wonderful than imagination. The ocean continues its ancient rhythms, tides rising and falling, currents flowing, waves breaking, organisms being born and dying, nutrients cycling, energy flowing, evolution progressing. These processes operated long before humans and will continue long after. But for now, in this brief moment of Earth's history, we have the privilege of understanding some of what's happening and the responsibility to protect it. The 2 hours we've spent together exploring ocean facts barely scratches the surface. We could spend 200 hours and still not cover everything, but perhaps we've shared enough to inspire wonder, to spark curiosity, to motivate action, to generate respect. The ocean is not mysterious in the sense of being unknowable. It's mysterious in the sense of being vast and complex. We can understand it piece by piece, fact by fact, study by study. Each fact we learn makes the ocean more, not less, amazing. So when someone asks what you know about the ocean, you can tell them about the creatures that reverse aging, the fish that can recognize faces, the whale whose heart beats 5 times per minute, the symbiosis between crabs and anemones, the bacteria that outnumber stars, the salt that would bury skyscrapers, the currents that flow like rivers, the civilizations built on maritime trade, and the species that recovered from near extinction. You can tell them the ocean is 71% of Earth's surface and 97% of Earth's water, that it produces most of our oxygen and regulates our climate, that it's home to millions of species most unknown to science, that it's been harmed by human activity but can recover with protection, that it's essential to all life on Earth, including ours. You can tell them the ocean is extraordinary, and now you know why. These are not myths or legends or exaggerations. These are facts, verified and documented, the reality of the ocean we share. May these facts inspire appreciation for the greatest feature of our planet and motivate action to protect it for future generations who deserve to inherit an ocean as magnificent as the one we've been privileged to know. The ocean has revealed its secrets generously to those who looked carefully. It has more secrets waiting to be discovered. The facts we've shared today are humanity's collective knowledge about the sea, gathered over centuries of observation and study. This knowledge is a treasure, a foundation for understanding, a guide for action, and a source of endless wonder. The ocean is real, the facts are true, the time to act is now. This has been 2 hours of amazing sea facts, realities that demonstrate how extraordinary our ocean truly is.